Hi everyone. Today I will be talking about design considerations and processes for battery-powered projects. When designing a battery-powered electronic project, it's good to analyze how long the battery is expected to last. Imagine if you made a project that monitors the temperature, but you needed to replace the batteries every single day. The project would be useless. You'd ideally want to keep the project running for weeks or months at a time with no intervention, not just hours. Sizing the battery should be one of the steps during the design process, not something left to after the design is completed. That means the desired battery life needs to be one of the design constraints, the same way input voltage and size are. Here I have a demo project. The project consists of a regulator, comparator, and LED subsystem. The project is made to demonstrate how to calculate expected current draw to find battery life. First, we will go subsystem by subsystem to find out how much current is needed, and then we will sum up the currents to see how long a selected battery will last. After that, we'll make some changes to the design to make the selected battery last longer. First, we'll look at the linear regulator. The linear regulator is taking the battery voltage and converting it to 5 volt. Besides the current it delivers, the only current draw this linear regulator is consuming is the IQ, the quiescent current. From the datasheet, we can see that this linear regulator consumes about 285 microamps of current, regardless of load. Let's confirm this by searching for quiescent current. Here we have two plots, quiescent current versus output current, and quiescent current versus input voltage. Here we can see that the quiescent current doesn't change much based on the output current draw. However, the quiescent current does change based on input voltage. In our case, the input voltage will be about 9 volts, so our quiescent current is going to be right around 300 to 350 microamps. So let's log that. IQ equals 300 microamps. IQ, that's 0.3 milliamps, and this regulator is always going to be on. Now let's look at our comparator subsystem. This comparator has two sources of current that it's consuming. One on the left in this resistive divider, and the IQ of the comparator itself. Let's start with the IQ of the comparator. From the datasheet, it's saying that the supply current is 3.2 milliamps. Let's confirm that by searching for IQ. When the voltage supply is 5 volts and VO is high, it's consuming about 3.2 milliamps typical and 5 milliamps max. So again, we will log this, 3.2, and this comparator is always on. Additionally, we have current draw from this resistive divider. We can calculate this current using Ohm's law. This current is 25 milliamps, and it is also on 100% of the time. Finally, we have our LED subsystem. The current in the LED can also be found using Ohm's law. The forward voltage of the LED when it is on is 3 volts. We're going to assume that there is a 0 voltage drop between the collector and emitter of the NPN transistor. So that means that the voltage drop across R3 is 2 volts. Using Ohm's law again, we get that the current is 2 over 100, which is 20 milliamps. So in the LED, it is consuming 20 milliamps, and it is doing it half the time, because the LED drive signal, if we trace it back to the comparator, this signal should be on roughly half the time due to the fact that we have a triangle wave centered at 2.5 volts being compared to a DC value of 2.5 volts. Thus, now we can start to sum the currents to see how much current the entire system is expected to draw. With all three subsystems, the total current draw is about 38.5 milliamps. Let's look at a battery to see how long the battery is expected to last. Here I have an arbitrarily chosen battery. The battery has a capacity of 860 milliamp hours. To see how long this battery lasts, we can divide milliamp hours by milliamps. With our current consumption of around 40 milliamps and the battery capacity of 860 milliamp hours, we only get a battery life of about 22 hours, or not even a full day. To fix this, we have two options. We can either A, get a larger battery, which is going to be more expensive, or B, reduce some of our current draw from the subsystems. Looking at each subsystem, the regulator is using very little current compared to the IQ and R div of subsystem 2. Subsystem 3 is using a lot of current, but it's being delivered directly into our load. It's not being consumed and dissipated as heat. Looking at the current in the resistive divider, if we increase the total resistance, we can decrease the current consumed. Let's do that by increasing the size of the resistors to 100K. Now we are consuming 25 microamps compared to the 25 milliamps. Already this more than doubled our battery life. Besides the LED current load, the next largest source of current is the comparator's IQ. The comparator chosen is a high-speed comparator with a very high IQ. If we choose a lower IQ comparator, at the cost of reducing the effective speed of the comparator, we can greatly reduce the current consumption. Instead of searching for a high-speed comparator, let's search for low-power comparators. This comparator is push-pull, can take 5 volts, and comes in the same package as the other one, and only consumes 5 microamps per channel. If we buy a single channel device, that's only 5 microamps. Now our battery is expected to last about 83 hours. With only 2 design changes, we more than tripled our expected battery life. Now we can see, besides the current in the LED, the biggest current consumer is subsystem 1's IQ. However, even if we reduce this to 0, we only get a marginal increase in the battery life. In fact, if we reduce everything but the LED current to 0, we only get 86 hours as opposed to about 85. The LED current is the hard limitation of our project now. If we wanted to further increase the battery life, we would have to make a compromise and deliver less current to the load. I hope this kind of analysis makes sense. It's very important and is often overlooked until it's too late to make meaningful design changes. Some careful consideration can save you hours of headaches and provide you hours more of battery life. Thank you for watching, and let me know if you have any questions.